Good afternoon all. This is Satish Kumar, Assistant Professor of EC Department. Now let us see the another video lecture series on linear time invariant continuous time systems in differential equation. See, let's explore. See, differential equation means how simplifying LTE system analysis by converting complex time domain operations into frequency domain multiplications, and how to design and analyze filters, control systems, and various signal processing tools. See, with the help of complex time domain operations, we can apply the differential equations and convert to frequency domain. By designing filters, we can analyze the control systems, and finally we can find out the efficient signal processing tools for differential equation. Empathy. Why differential equations? See, differential equations describe how output depends on present and past inputs. In RC circuit voltage, response is governed by differential equations, and how do we see signals in systems as interconnected equations. Next one, this is the defined part of differential equation. It is used to represent continuous time linear time invariant system. It relates the input and output of the system. When x of t is applied to differential equation, which can produce as output as y of t. The input signal, the system receives an input signal, then the system processes the input signal, and the system produces the output signal, and the output signal may be influenced to the for future inputs. This is the major role of differential equation. Next one, time domain into frequency domain. For linear differential equation, we can apply the Laplace transform. We can convert it into Laplace transform in for equation, and then solving for roots and find out the algebraic function, we can get the Laplace solution. And finding the inverse Laplace transform of Laplace solution, we can convert it into time domain solution. This is the sequence for time domain into frequency domain. See, system transfer function is defined as the ratio of the output to the input. H of s is equal to y of s divided by x of s. Frequency response, it can be replaced by omega, is called as frequency response. H of omega is equal to y of omega divided by x of omega. When x of t is applied to Fourier transform, which can produce output as x of omega. Frequency domain analysis, h of omega, which can produce the output as y of omega. We can apply the inverse Fourier transform of y of omega, which can produce the output as y of t. Next one, this is the ideate function of differential equation. First, differential equations describe the system behavior, and we can going to analyze the linear time invariant systems, and we can apply the Laplace transform. Finally, we can get the impulse response of the system. This is the flow chart. First, for the differential equation, we can apply the Laplace transform and finding the algebraic equation, and then solving for roots. We can apply the inverse Laplace transform. We can get the impulse response sequence. Next one, every LTA system can be described by the linear constant coefficient differential equation. It can be solving by using differential equation with the input del of t, which can give h of t. Impulse response h of t completely characterize the system. The differential equation is then effectively a generator of impulse response. See, this is the prototype of convolution. Complex exponential serves as a fundamental building blocks, revealing that the LTE system responds to different frequency components of the signal. Impulse response h of t characterize the system. Convolution in the time domain corresponds to the multiplication in the frequency domain. For the complex exponential, we can identify the fundamental building blocks of signal analysis, and then impulse response, how to react with the impulse input, and finding the convolution for time domain analysis, and then that can be converted into frequency domain by using multiplication, simplifies the convolution analysis. Next one, testing part. Set the input to the unit impulse x of t is equal to del of t. Then the output we can get it as your impulse response h of t. Converts differentiation into multiplication, that is d by dt, which tends to s, which is much easier. Directly gives the h of s, whose impulse response, whose impulse transform is h of t. Right? First, we can apply the unit impulse function. You can initialize the process. Next one, we can obtain the inverse transform, convert the transfer function back into time domain, and then we can obtain the transfer function, derive the transfer function from the frequency domain, that can be transformed to frequency domain, convert the response to frequency domain. Finally, we can get the observe the output. We can get it as your system response to the impulse. Next one, these are the applications of differential equation. It is used in system response analysis, control systems, signal processing, communication systems, biomedical applications, and transforming methods. See, system modeling, creating mathematical representation of systems and studying how systems react to the inputs, and also we can design systems to manage the regular process, and then analyzing and manipulating signals, developing systems for transferring information with the help of communication systems, applying differential equations in healthcare for biomedical applications, and then using transforms to solve the differential equations by various transforming methods. Now we can see the assessment. Define differential equation. See, differential equation relates the input and output of the system. System transfer function is given by h of s is equal to y of s divided by x of s. See, convolution in time domain corresponds to multiplications in the frequency domain. Define unit impulse signal. It can be represented as del of t, where that can be applied to the impulse response. We can get it as your impulse response of the system. Impulse response h of t is obtained by taking inverse Laplace transform of h of s. Thank you.